Hello everyone, this is the first video of my USA Physics Olympiad tutorial series. In this video I will be covering how I approach problems and the A1 problem of the 2013 semifinal exam. So in each video I'll assume that you've already read the problem and have some basic understanding. Alright, so let's start with this problem. Problem A1 deals with thermodynamics. In this problem, there's a heat exchanger device. You have a cold fluid flowing through the slab on the top, and a hot fluid flowing through the slab on the bottom in the opposite direction. So, in this problem, initially the temperature difference between the entering fluids is delta Ti. And in this diagram, see, the first thing I do is I label unknowns with variables. In this problem, we need to find the final temperature difference, which is the difference between the temperatures of the exiting fluids. Since we don't know these temperatures, and we don't know the difference of the entering fluids is also given, because we don't know the actual temperatures of the entering and exiting fluids, I would label them with variables, TB final and TB initial. And I've avoided putting a little zero here just to make writing a little simpler. And same with the red. Notice that the hotter fluid, the TR final, is over here instead of over here because the fluids are flowing in opposite directions. So the first thing I like to do is to take the given constants and write them in terms of the labels I put on the diagram. So delta Ti, what is that? That is equal to the entering difference between the entering fluids. So that would be TR minus TB. Now we're also given the final temperature difference, delta T final. That's equal to simply TR final minus TB final. So these are the given. This entire diagram, all these labels are given, except for these four temperatures. We're also given the constant of thermal conductivity, K. We're given also the heat capacity, C. Alright, so the first step, and I don't want to miss this one, they also give a equation for power, which is the power when transferring energy from one slab to the other. It's equal to the thermal conductivity constant times the area times and this is simply the change in temperature between one slab to the other slab. And I believe yes, they say that the temperature difference across the wall is the same everywhere, and that we don't need to prove that. So that's something to keep in mind. And the power here, the delta T they use, is the difference of the two faces. So that would be, let's let the difference of the two faces be called delta TW. And that's all over distance. Alright, so the first step in solving this problem is to take what we have and to expand on it. So we know this delta T final. That's what we want, right? Delta T final. So let's write that over here. Delta T final is equal to TR final minus TB final. Now, when I'm working with problems, I like to reduce the number of variables and to make the problem as simple as possible. I mean, it's definitely doable with more variables, but it's going to take a lot more work, and I'm not entirely sure if this problem is doable with only with 4 variables. So, and even in algebra, I like to eliminate variables. So let's say we didn't want to use TB final and TR final. We only wanted to use TB and TR to make it nice and simple. So what is TR final? TR final over here. And since we do know that there is a constant temperature difference between the faces, TW, we can say that TR final is equal to TB plus TW, because that's the difference. TB plus TW. And what is the temperature difference of the TB final? That is equal to simply TR minus that constant difference. Which would give us TB final. So this is also equal to TB. Well, first of all, TB minus TR. Oh, we've seen that. It looks similar to this over here. Looks similar to this. Except it's the opposite of that, right? The opposite of this would give you that, which is TB minus TR. So we can write negative delta I, delta TI. Great, so we've already used one of the constants that they have given. And now this part, plus 2 TW. And now you get stuck at this point, and you say, well, we're not given. If you read the problem, we are not given what TW is. But look over here, the power equation. We are indeed given a way of solving for TW. So let's write that out. P power equals K, which is given, the area, which is the area of one of the faces, length times width. And then times delta TW over D, which we are also given, the distance between the faces. When you get to this point, you're going to say, or maybe some of you will say, we're not given the power, so then what do we do beyond here? Well, let's look at the equation. What does the equation mean? It means the change in energy over change in time. Remember that power is work over time. So the transfer of energy, the change in energy over time, d dt, is equal to power. So if we move dt to the other side, we get dE equals p dt. And do keep in mind that you will need to have some understanding of calculus to do the USAPHO problems. dE equals p dt. And the reason why I turned this into a expression of dE is because in thermodynamics, there's also another equation called Q equals mcat. You see, in this equation we have two unknowns, TW and P. And the way to eliminate two unknowns is to come up with another equation and try to equate them and solve for one of the variables. So we do know that Q equals mcat. So what is Q? Q is the heat energy that is transferred. Alright, so Q is... Oh no, wrong color. Alright, so this is the heat energy transferred. M is the mass of the fluid. C is the specific heat. Now there is a difference between the specific heat and the heat capacity. Specific heat is per unit mass. So that is exactly why we multiply it by the mass. So that we know what the total is. So this is specific heat. And delta T is the change in temperature of the fluid that we're looking at. Change in temperature of fluid. So in this problem, our little change in heat energy, dE, is equal to, since we have heat capacity, and in the problem it does state that this is heat capacity per unit volume. So what we're going to have to do is we're going to have to multiply our heat capacity by similar to how the specific heat is multiplied by the mass. Alright, so in a small time dt, the volume would be the width times the height. Remember, we're looking at the hot fluid slab times the height. And we want to know that little tiny distance dx, right? Since to get the volume, it's length times width times height. So that dx would become, since we're given v, we can write that as v dt. And then we write down our heat capacity, C1, and delta TR, which is the change in temperature of that fluid. Delta TR. Alright, so now we have two equations, and we're thinking of equating them, but we don't know what delta TR is. So how can we write this? How can we write delta TR in terms of what we know? Well, delta TR is simply our initial state, which is TR, minus our final state, which is TR final. And I believe we already found what TR final is up here. So we can write delta TR as TR minus TB plus TW. And what is TR minus TB? Oh, it's delta TI over here. So that's delta TI minus delta TW. So at this point, we can simply equate both sides. We can set this quantity equal to this over here. And we can divide out the dt's. So without the dt's, it would look something like this. K LW delta TW over times WHV C1. And we'll leave it as C, because the problem does call it C. C times delta TR, which is delta TI minus delta TW. And I do want to keep this video short, so this is just simple single variable algebra, and when you solve for delta TW, you will get that delta TW is equal to delta TI over 1 plus KL all over D, all over D VHC. And in the end, we do have our equation for our final difference in temperature, which is negative delta TI, which is the given constant, plus 2 times this delta TW that we have found. And again, to save time on the video, to keep it short, you get through some simply by plugging this value over here and rearranging the equation, you get delta T final equals delta TI times 2 over 1 plus KL over DVHC minus 1. Alright, so now I'm going to talk about why this final answer makes sense. So as you can see here, this entire quantity delta TF is controlled by this dimensionless constant over here. Now it makes sense because the better performance you have, the less the difference in the exiting temperatures of the fluids. And that makes sense because if you have longer tubes and you have better thermal conductivity constant, that will result in a greater denominator, which means that the temperature difference would be less, which means higher performance.